Testing, can you hear me? Hello? This stream is unlisted right now. It's not public yet. Hello everyone, can you hear me? I'm going to be reading about multiple integrals again. So I'm going to be studying calculus again. And I'm going to be reading about multiple integrals. Last stream, hold on a minute. Let me just change to full screen. Yeah, so last stream I read about the center of mass thing and moments of inertia. This stream I'll be learning about change of variables and multiple integrals. Right. So this is just going to be this chapter. Recall from the substitution rule the method of integration by substitution. When evaluating an integral such as this one, we substitute x squared minus 4 and du becomes 2x dx, or x dx is half du. The limits change. The integral becomes this. This integral is much simpler to evaluate. In other words, when solving integration problems, we make appropriate substitutions to obtain an integral that becomes much simpler than the original integral. We also used this idea when we transformed double integrals in rectangular coordinates to polar coordinates and transformed triple integrals in rectangular coordinates to cylindrical or spherical coordinates to make computations simpler. More generally, we have from A to B comes from C to D. So we have f of 0. A similar result occurs in double integrals when we substitute x is equal to h r theta, which is equal to r cos theta, and y is equal to r sin theta, and dA is equal to dx dy, which is r dr d theta. Where the domain r is replaced by the domain s in polar coordinates. Generally, the function that we use to change the variable to make the integration simpler is called a transformation or mapping. A planar transformation T is a function that transforms a region G in one plane into a region R in another plane by a change of variables. Both G and R are subsets of R squared. For example, figure 5.71 shows a region G in UV plane transformed into a region R in the XY plane. So UV over here transformed to XY. by the change of variables x and y. We shall typically assume that each of these functions has continuous first partial derivatives, which means gu, gv, hu, and hv exist and are all continuous. The need for this requirement will become clear soon. A transformation defined as tuv is equal to xy is said to be one-to-one transformation if no 2 points map to the same image point. To show that T is a one-to-one transformation, we assume Tu1v1 is equal to Tu2v2. Ensure that as a consequence, we obtain U1v1 is equal to U2v2. If the transformation T is one-to-one in the domain G, then the inverse exists with the domain R such that T to the power, the inverse of T dot, I forgot what you call this. Inverse of T and T and inverse of T are identity functions. Figure 5.7 shows the mapping of TUV is equal to xy where x and y are related to u and v by the equations x is equal to GUV. Okay, so we have u here, g here, we have uv point, and x is equal to GUV. Over here we're planting the x, y is equal to HUV, then we are planting the y here. The region G in the domain of T and the region R is the region G is the domain of T. The region R is the range of T. Okay. Also known as the image of G under the transformation T. So this is the image of T, image of G under the transformation of T. Suppose a transformation T is defined as T r theta is equal to xy, where x is equal to r cos theta, y is equal to r sin theta. Find the image of the polar rectangular G in the r theta plane to a region R in the xy plane. Show that T is a one-to-one transformation in G and find T minus 1 xy. Okay, hold on. Capture area. Copy. So T r theta G is r theta, r from 0 to 1, theta is from 0 to pi over 2. So T is from G to R, right? Example 5.65. Then G is defined like this. If G is equal to r theta 0, 1, 0 from pi over 2, then R. So all the R values go to X, right? And all the theta value goes to Y. Is 0, X, 1, and 0, Y, pi over 2. So that means T minus 1 xy is equal to r theta. We know this is 1 to 1 because for every unique value of r and theta gives a unique value, gives a unique pair. The pair, yeah. Oh, where x is equal to r cos theta, I got this wrong. X is equal to r cos theta, y is equal to r sin theta. I don't know why I read this. Sorry, I read this as x is equal to r. Wait, this is all wrong. X is equal to r cos theta, y is equal to r sin theta. So maximum value of x is from, so minimum it can be 0. No, minimum it can be -1. That's the lowest value possible for x. The highest value possible is +1, right? Cos theta can be 1, same for y. -1 and 1. Doesn't that mean 0? No, -1, -1. Isn't this the transformation? T of -1 xy gives you r theta, where r is equal to uh, and theta is equal to hold on, cos theta, y is equal to r sine theta. Could write y as x cos theta sine theta, right? And instead of r, I'm writing this. And then sine divided by cos becomes tan. Tan theta. And then theta is like that. Yeah, so x square is r square cos square, y square is r square cos square. If you add them up, get s square plus y square is equal to r square. And cos and sine, cos square plus sine square, that is equal to 1. So you end up with this. So since r varies from 0 to 1 in the r theta plane, your circular disk radius r to 0 in the xy plane. Because theta varies from 0 to pi over 2 in the r theta plane, we end up getting a quarter circle of radius 1 in the first quadrant of the xy plane. Hence, r is a quarter circle bounded by x square plus y square is equal to 1 in the first quadrant. In order to show t is 1 to 1, assume that t is equal to t r1 theta 1 is equal to t r2 theta 2. We do this, we get this, we get this. r1 cos theta 1, r2 cos theta 2. Dividing, we obtain. What do you mean dividing? For dividing these two, we obtain r1 cancels out, r2 cancels out. We get that the theta are different. Since the cotangent function is one-to-one function in the interval 0 to 2 pi over 2, and since r is between 0 and 1, we have r1 is equal to r2 and theta 1 is equal to theta 2. Therefore, this is equal to this. Okay, so that's how they showed it's one-to-one. So the inverse is t minus 1 xy gives r theta, where it's defined as r is equal to this and then theta is equal to this. Let the transformation t be defined like this, where x is equal to u square minus v square and y is equal to uv. Find the image of the triangle in the uv plane with vertices 0, 0, 0, 1 and 1, 1. So the triangle is defined in the xy plane, right? 6.6, 5.66. So in the xy plane, we have 0, 0, we have this 0, 0, 0, 1, 1, 1 in the xy plane. And we want the image of the triangle in the UV plane. U and V. Just to be sure, triangle is okay, I was wrong. The triangle is defined in the UV plane. Okay, I can't tell whether this is saying image of the triangle in the UV plane or the triangle in the UV plane, and we're finding the image of the. I can't tell whether the image is in the UV plane or UV plane or whether only the triangle is in the UV plane. But that was my mistake. U, U, V, 0, 0, 0, 1 and 1, 1. You want to find how it looks like in the xy plane. X is equal to u square minus v square. Y is equal to UV. So so point 0, 0.00 in the UV plane is 0.00 in the XY plane, 0, 1, 0. V is 1, right? So Y is also 0. V is 1, U is 0. Oh, so it's a negative 1. We have 1 over here. We have 1 minus 1, 0. So we have 0, 0. Okay, wait, let me think of another way. So 0, 0, 0. Oh my gosh. 0, 0 here is 0, 0 over there. 0, 1 here is minus 1, 0 over there. And then, wait, this is minus 1, 0. So 1, 1 here is 0, 1 here. And then we have 0, 1 over here. It's minus 1, 0 over here. I don't know if it's 1 to 1. Here, this goes here, and this goes here. Let me just check again. So 0, 1. 1 times 0 is 0. And then we have negative 1 here. Then I am confused. 0, 0. 0, 1. 1, 1. Let me think. Call the side that joins 0, 0 and 0, 1 side A. So side A is just U is equal to 0 for, okay. So what they're doing is, uh, what they're doing is side A, B and C. A is u is equal to 0, and we have this. So u is equal to 0. So y would be 0 in the entire thing. And from 0 to 1, x would go from 0 all the way till -1. 0, 0 to 0, 1. 0, 0 to 0, 1. Y is equal to 0 and x will go all the way. Okay. Side B. Actually, there's two side C for B is equal to this. And so now what? V is 1. So y goes from 0 to 1. Y would go from 0 to 1. V remains 1. Now V over here is 1. So we have -1. -1. X goes from 0 to -1. Right? -1 here. Okay. And then for side B, which is y is equal to x. Sorry, we have side B, which is u is equal to v. We have v square. Right. From 0, 0, 0 to 1, 1. So from 0 to 1. Let's just figure out the y. The y goes from 0 to 1. The x goes from, no, the x just stays 0. So side B, x is 0. Y goes from 0 to 1. X remains 0, y goes to 0 to 1. For side C, for side A, y is at 0, x goes from 0 to -1. For side C, y goes from 0 to 1. However, x goes from -1 to 0. But I don't think it goes linearly because it's like u square minus, it would be -1. If I have, I don't know how to explain this. Y would go from 0. When y is 0, x is -1. When y is 1, x is 0, but not linearly. More like this. This is for side C, right? Transforms this. So this is side C sharp, C apostrophe. That makes upper half of the parabolic arc joining minus 1, 0 and 0, 1. But how would you like explain this though? V is 1. So like u square negative 1. Y is just u. So is y square negative 1. Y is equal to root x plus 1. 1 and then root. Yeah. X plus 1. Okay. This graph follows that. That's how you would explain it. Jacobians, recall that we mentioned near the beginning of this section that each component function must have continuous first partial derivatives, which means gu, gv, hu, and hv exist and are also continuous. A transformation that has this property is called C1 transformation. Here C denotes continuous. Let T uv is equal to G uv, H uv, where X is equal to GUV and Y is equal to HUV. Be a one-to-one C1 transformation. We want to see how it transforms a small rectangular region S delta U units by delta V units in the UV plane. Okay. Since X and Y, since X is this and Y is this, we have the position vector R UV is equal to GUVI plus HUVJ of the image of the point UV. Suppose that U naught V naught is the coordinate of the point at the lower left corner that mapped to U naught V naught is equal to T U naught V. I'm saying U naught. X naught Y naught is equal to T U naught V naught. The line V is equal to V naught maps the image curve with the vector R U V naught, and the tangent vector at X naught Y naught to the image curve is this. This is getting complicated. So partial derivative of x with respect to u plus partial derivative of y with respect to u. And this is just what are we finding? The vector function are okay. So this is v naught. This entire thing is at v naught. So this line maps to this line, and this single line is represented by r u v naught. But why are we representing it like this? Okay, so this is the partial derivative of r with respect to u. So RUV is defined like this. Taking the partial derivative with respect to u is defined like this. You take the partial derivative with respect to u independently, and it's defined like this. Similarly, the line u is equal to u naught maps to the image curve with vector function r u naught v, and the tangent vector at x naught v naught to the image curve is this. So wait, hold on. The tangent vector. Okay. So position vector and tangent vector. Tangent vector means we are taking the derivative with respect to whatever the thing is. So this we are taking the derivative at position x naught, y naught. Now note that we have this. So hold on, what's going on? So this with respect to u at position at this position, taking we are taking r, tiny increase in u. Yeah, right. Okay, by the definition of derivatives, you're doing this. So r u naught plus theta. Okay. So this part is roughly for a very small delta u. This, how do I get rid of the highlight? The numerator is approximately equal to delta u derivative of r with respect to u. The same thing for b. This allows us to estimate the area of the image R by finding the area of the parallelogram formed by the sides, this and this. Okay. By using cross product of these two vectors by adding the k component as 0, the area delta A of the image R is approximately delta U R U cross product delta V R V. In determinate form, the cross product is, we have this. But what is k over here? I forgot. Adding the k component as 0. Oh, there are 3 dimensions, but we aren't considering the z axis. Since the length of k is 1, how is the length of k 1? K is like 0, 0, right? By using cross product of these two vectors by adding the k component. Okay, since this is 1, we have delta A is equal to delta x over delta u, delta y over delta v minus delta x over delta v, delta y over delta u, delta u, delta v. I don't understand this part. This allows us to estimate the area of the image by finding the area of the parallelogram formed by the sides, this and this, by using the cross product of these two vectors by adding the k component as 0. The Jacobian of C1 transformation TUV is denoted by JUV and is defined as a 2 by 2 determinant. The Jacobian is delta xy over delta uv. Uh, delta x, delta u. Using the definition we have, so delta area is Jacobian, delta u, delta v. What is this division thing over here? I don't remember seeing this in the matrix chapter. Now that the Jacobian is frequently denoted simply by this. Note also that if this, okay, this is by definition of determinant. This times this minus this times this. Hence, the notation suggests we can write Jacobian determinants with partials of x in the first row and partials of y in the second row. Find the Jacobian transformation given in example 5.6.5, 5.6.5. How do I find the Jacobian? So this is Jacobian is, okay, let's just try it. I do not understand it, but let's just try it. I don't understand the derivation. I think when the derivation is confusing, the everything else becomes confusing. So the Jacobian UV is equal to uh, so so we have x in the first and then y in the second. Wait. U and then v. This is the Jacobian, right? UV. But here's the thing. Jacobian with, you're doing it with r and r theta, right? R theta, r theta. X over r is like respect to r is just cos theta. With respect to theta, derivative as cos is minus sine theta. R y is r sine theta. So then we are left with sine theta because r will just disappear. And then cos theta. This times this So cos theta times r cos theta minus this times minus this times this minus r sine theta sine theta. Minus sine becomes plus r sine square theta. But then this is just r. 5.66. Never mind, I'm too lazy. Change of variables for double integrals. I've already seen another change of variables. T U V X Y. Small region delta A in the xy plane is related to the area formula by the product delta U delta V in the UV plane by the approximation this. Now let's get back to the definition of the double integral for a minute. You have this double integral, you have this definition. Referring to figure 5.75, observe that we divided region S in the UV plane into small subrectangle Sij. 5.75. Okay, over here, we divided the region S into small planes, and this is one of the plane. We let the subrectangle Rij in the xy plane be the image of Sij under the transformation TUV is equal to xy. Then the double integral becomes this, and the double integral becomes instead of x and y, they're writing the g of uv in h of uv. And instead of delta a, they're writing this. Notice that this is exactly the double Riemann sum for the integral. This. Okay, this is getting pretty complicated. With this theorem for double integral, we can change the variables from xy to uv in a double integral by simply by replacing delta dA dx dy, which is Jacobian du dv. So to find the area xy, you find the area in S. But we don't want from xy to uv, we want from uv to xy, right? Let duv is equal to xy, where x is this, u is this, be a one-to-one transformation with a non-zero Jacobian on the interior of the region S in the uv plane. It maps S into the region R in the xy plane. It maps S into the region R, okay. If f is continuous on R, then you have this. Consider this integral. Use the change of variable. X is equal to r cos theta, y is equal to r sin theta. Find the resulting integral. 5.69. dy dx. Now how do we change the regions though? No. dy dx. X is equal to r cos theta. Y is equal to r sine theta. Find the resulting integral. So y is this, x is this, and we change this to Jacobian. You already know the Jacobian is r, right? Because we did that before. X 0 means okay. You have region R, x square, y square. Region S, r cos theta plus r sine theta. Sorry, r square cos square theta, r square sine square theta. You're just left with r. And then Jacobian of this is r. And then dr d theta. But then what about the variables on top though? Okay, they got the r squared, that's right. Squaring and collecting terms, we find that the region in the upper left of the circle is x square plus y square minus 2x is equal to 0. That is, y square is equal to x minus 1 square is equal to 1. In polar coordinates, the circle is r is equal to 2 cos theta. So the region of the integration in polar region is bounded by 0 to 2 cos theta, 0 theta pi over 2. So theta is between 0 and pi over 2, r is between 0 and 2 cos theta. But how do we get this algebraically? Like if it was complicated and we did not have the graph, how would we get it then? So the resulting integral is this. Consider the integral x minus y dy dx, where r is a parallelogram joining the points 1, 2. 1, 2, 3, 4, 4, 3, and 6, 5. Make the appropriate changes of variables and write the resulting integral. The region of integration is here. What do they mean make the appropriate changes of variables? Do I turn it into a rectangle? First, we need to understand the region over which we integrate the size of a parallelogram. X minus 1 plus x minus y plus 1 is equal to 0. Which side is this? I think it would be easier to understand if it was written in terms of y. So the first one is y is equal to 1 minus x, right? No, minus 1 minus x maybe. Okay, we have these four equations. Another way to look at them is this. Clearly, the parallelogram is bounded by the lines. Bounded by these lines. So then what are these equations? 4, 2, 4, 3, 4. We have 1, 2. Are these lines drawn wrong? What? Shouldn't 4, 3 be here? 3, 4, 6, 5. What is this line? Size of the parallelogram are these four equations. Another way to look at them is this. Clearly, the parallelogram is bounded by these lines. If we put y to the other side, we get y is equal to x plus 1. Here we get y is equal to x minus 1. Yeah. Okay. Notice that if we were to make u is equal to x minus y and v is equal to x minus 3y, then the limits of the integral would be minus 1 to 1, minus 9 to minus 5. Why are we choosing this? To solve for xy, we multiply the first equation by 3 and subtract the second equation. Then we have this. Moreover, get this. Then we can choose this transformation. But I don't get why they chose this. Why they chose these two? Why even u and v values? So choose transformation, determine the new limits, find the Jacobian, in the integrand replace the variables. Replace dy dx or dx dy, whichever occurs by this. But the thing is, what I don't understand is the limits of the integral. These two, how do we determine this, like purely algebraically? Uh, so example 7.5.71. This looks ugly. We have r x minus y e is equal to x square minus y square dA u x minus y. X plus y. Uh, then we can write this as so we have integral s u e to the power of uv Cobian uv du dv. And then we have uh hold on. U is equal to sorry x is equal to u plus y, which is equal to u plus v minus x. And then similar for y, v minus x, v minus no, u plus y. So then this integral respect to u, hold on. Isn't it just half? X is equal to u over 2 plus v over 2. With respect to u, this part is 0. Derivating this part is just half, right? This is also half. This is minus half. This is half. So then these two multiplied together. Half and half is 1 over 4. Minus these two, so plus these two, 1 over 4. Half. And what are we doing? That is the region bounded by these two lines and the curves. X square minus y square is equal to -1 and x square minus y square is equal to 1. Um, so then uv goes from -1 to 1 and v goes from 1 to 3. Then that means u must vary from from if v is the largest number, which is 3, and then u is -1 over 3, then we will get -1, which is the smallest number. If v is 3, then u can be 1 over 3, which would give 1. I think that makes sense. I think it would be easier if you integrate v first. Now, derivative is this, right? I'm forgetting a lot. This the derivative won't change. And this derivative will just be u. So that means 1, 2, 3. The integral of this with respect to v gives this. So let's take the half out. With respect to v, we are left with we are left 3 minus 1, right? Uh, no, I don't know what I was thinking. Actually, minus it with, okay, I don't want to do this, but I need to know if I'm heading in the right track. V goes from 1 to 3. Okay, we write this as u going from minus 1 over v to 1 over v. And we integrate with respect to u first. Okay. If I continued this, never mind, I will just see it off screen. Changing variables and triple integrals works exactly the same way. So cylindrical and spherical coordinate substitution are special cases of this method, which we demonstrate here. Suppose G is the region in UVW space and is a map to T in the XYZ space by one-to-one transformation, where X is equal to G UV and Y is equal to H UVW. Z is equal to K UVW. Then any function defined on D can be thought of as another function that is defined on G. Now we need to define Jacobian for 3 variables. Uh, it is simply denoted like this. Oh my god. So we have F, then the Jacobian du, dv, dw. Yeah, I'll just read. Okay, that's it. Uh, Let me just read through this. For cylindrical coordinates transformation, r theta z to is equal to xyz from Cartesian, r theta z to Cartesian xyz here. Z is equal to r cos theta, y is equal to r sin theta, and z is equal to z. Jacobian for the transformation is this, and we are left with r g r dr d theta dz. For the spherical plane is yes, we have rho theta phi. Rho is the length, right? And theta is from the x, and then phi is from the z. Okay, I think I will read this one off stream. And I will, okay, this was quite a complicated chapter. I think this was, uh, maybe this was the hardest part so far, what I've done in the calculus, the Calc 3 book. Anyways, I will end the stream here and I will continue reading. I'll probably read discrete math in the next stream. But yeah, I will continue tomorrow then. Probably with discrete math. Anyways, see you guys next time. Bye.